and Surendra Pradhan. We can't hear you, but we can see you.
Okay, now, yes, I am here. Now, maybe I can.
You are very welcome, all of you. Thanks a lot. Then we will get back to the normal old-fashioned procedure again, I think. The title of the thesis is Alkaline Urine Dehydration, How to Dry Source-Separated Human Urine and Recover Nutrients. My name is Per-Anders Hansson. I am professor at the Department of Energy and Technology, and I have been appointed by the faculty to share this session. Now a more formal welcome to the opponent, Dr. Nancy Love from Department of Civil and Environmental Engineering in Ann Arbor, Michigan, US. And welcome also to the members of the Evaluation Committee, Professor Anneli Hedström from Luleå Technical University in Sweden, to docent Sebastian Svede, Mälardalens högskola, Västerås, Sweden, and to Dr. Surendra Pradhan from the University of Eastern Finland in Kuopio, Finland. You are all very welcome to this event. And also welcome to docent Åke Nordberg, which will be the reserve in the Evaluation Committee. Åke is from the Department of Energy and Technology here at SLU. The schedule for today will be that Prithvi will talk for about 30 minutes, I think. Then I leave the word to the opponent, and then I leave the word to the Evaluation Committee, and finally to the audience. And it's also handled that if you are on a link as audience, you will be able to put questions in the chat, I think. And then I will close this session, and I can come back to what will happen afterwards. I also want to announce from the start that we will have a break, a pause after 90 minutes. If it's not very close to something, but around 90 minutes, we will have a short pause. And then, before I leave the word to Prithvi, I want to ask you if you have anything to add to the thesis.
Yes, I have an errata list that I've sent to the committee and will be made available on the Zoom chat as well.
Perfect. Then I think all formal things are ready, and now it's your time to speak.
Thank you. So, hi and welcome to my dissertation seminar. My story begins in the year 2015. 2015 was the year that I started a master's program in environmental science. For me, this was a big change because I was a chemical process engineer. But 2015 was also the year that the world shifted from the Millennium Development Goals, the MDGs, to the Sustainable Development Goals, the SDGs. And we set ourselves an ambitious goal to provide clean water and sanitation for all people by the year 2030. Unfortunately, by the UN's own latest estimate, our current progress on the SDG 6 is alarmingly off track. Today, billions still don't have access to safely managed drinking water or sanitation systems where fecal sludge or wastewater is collected safely, treated properly, and discharged safely again. This means that if things continue as usual, we are not likely to achieve SDG 6 come 2030. But if we are to accelerate our progress on SDG 6 and on Agenda 2030, we will need out-of-the-box innovations in sanitation. But what we often forget is that an innovation in sanitation can have a big positive impact far beyond the bathroom in which it is implemented.
Recording in progress.
For instance, let's consider the use of nitrogen in the growth of food or protein. Today, the majority of the nitrogen we apply in agriculture as fertilizer is produced using the HABER-BOSCH ammonia process. but only 4 to 14% of the nitrogen that we apply on our agricultural field actually ends up in the human body as consumed protein. Now, as adults, we don't even retain this nitrogen. We instead excrete it. And we excrete it mostly via our urine. Which means if we don't treat our urine properly, then nutrients in the urine, such as nitrogen and phosphorus, they can diffuse into the environment, where they can contribute to eutrophication, acidification, and global warming. So in the coming years, yes, we have to improve the overall nitrogen use efficiency all along our food chain. But we also need to find and develop methods to close this nitrogen loop by recycling nitrogen back into our food systems. And one way we can do this is by recycling urine, because every year, each of us excretes about 4 kilograms of nitrogen, 1 kilogram of potassium, and half a kilogram of phosphorus via our urine. But as you see, urine is mostly water by composition. And because of this characteristic, recycling urine from cities, where most of the world population lives today, to rural cropland where we need these fertilizers in agriculture, these distances can make this recycling process prohibitively expensive. And this especially depends on where you live in the world today, because these transport distances can vary from a few kilometers to a few hundred kilometers. But this whole service chain around the collection, the transportation, and the application of urine in agriculture, we can make this relatively simple if we separate the water from the nutrients present in the urine. And this is exactly what I investigated in my PhD education by looking into the different processes involved in treating source-separated human urine by this technology of alkaline dehydration. Specifically, I developed methods to stabilize urea and prevent its hydrolysis in urine. I optimized the recovery of nitrogen when I dry the urine. I evaluated the fate of different elements, as well as the quality and the composition of the fertilizer that I produced by drying urine. And I provided insights into which helped in the understanding of the dehydration process. And overall, I have demonstrated through this thesis that this technology of alkaline dehydration can be scaled and can be implemented in practice. So my thesis is based on 5 published papers. In the first 3 papers, I developed and evaluated the technology in the lab. In the 4th paper, I built a pilot-scale urine dryer, which I implemented in the field. And in the 5th paper, I present the overall concept of drying urine, where I also put forward arguments supporting the fact that this technology can be integrated into existing systems to complement existing infrastructure. So part 1, alkalizing urine. When we excrete urine, fresh urine has a neutral pH. But when we collect this urine in a urine separating sanitation system, an enzyme called urease, which is produced by bacteria that colonize our piping systems and our plumbing network, this enzyme can degrade urea, which is the major nitrogen compound in urine, and produce ammonia, thereby hydrolyzing the urine. Which means if I try to dehydrate hydrolyzed urine, then I don't capture nitrogen because we lose it as ammonia gas. But we also know that this enzyme is not active at pH values above 10. So in my studies, I was interested in alkalizing fresh urine in order to prevent this reaction from happening, so that I preserve the nitrogen in urine in the form of urea, so that when I dry the alkalized urine, I don't lose this nitrogen. I tried 2 different ways of alkalizing urine. In the first approach, I used an ion-exchange resin. And here, the thinking was that we would place this resin inside the bowl of a urine diverting toilet, so that when urine passes through this resin, the anions that are naturally present in urine, such as chloride, they could be swapped with the hydroxide ions present on the resin, thereby alkalizing the urine, so that it can be transported via pipes, say to the basement of the building, where we can dry the urine without losing the nitrogen. In the second approach, I added fresh urine directly to different alkaline substrates. And here the thinking was that we would eventually develop a urine dryer which contained these substrates, and we would place this dryer immediately next to the toilet so that fresh urine could come in, get collected, stabilized, and dried on the site. So my first task, or my first step, was to understand how much resin I needed to alkalize the urine. And I found that I needed a resin dosage of 20% by volume of urine in order to alkalize it. But when we place this resin inside the bowl of the toilet, in practice, not all the urine might pass through this resin. So I also identified that a minimum of 75% of the urine needs to pass through this resin for the pH to go above 10. And remember that we need this pH of 10 in order to inactivate the enzyme urease. But overall, the results of my ion exchange studies also showed that in order to alkalize all the urine that a family of 4 produce in a month, we would need about 36 liters of resin, which means that not only would the resin occupy quite a lot of space in our bathrooms, it would be too expensive. And for this reason, I abandoned the resin from the first study in favor of the second approach, where I added urine directly to different alkaline substrates. And this was because I found that simply by adding a few grams of compounds like magnesium or calcium hydroxide, I could raise the pH of urine from below 7 to above 10. And for a family of 4, it would cost less than $5 to buy all the substrate that they need to alkalize all the urine that they produce in a year. So this approach also had a more universal appeal. Next, I was interested to, of course, investigate how I could dry this alkalized urine. And in the lab, I did this by modifying an incubator oven, which I operated at different temperatures, and by drying urine in Petri dishes which contained the different substrates. In the field study, I built a pilot-scale urine dryer, which I integrated into an existing portable dry sanitation system, which is the Biomaya toilet. It's the pink cubicle that you see in this picture. And I did this by placing a urine dryer into the toilet cubicle, and the urine dryer essentially consisted of a series of 3 interconnected boxes. In each box, we placed a mixture of calcium hydroxide and wood ash, and then we covered these boxes with lids which contained fans, and these fans provided heat and ventilation for doing the drying. And the whole system was connected using pipes to the existing dry urinal, as well as the urine separating toilet inside the Biomaya cubicle. And this system, on paper at least, had the capacity to dry 30 liters of urine per day in less than 1 square meter area that you see over there. And which means that over a period of 1 month, we had the overall capacity to dry 900 liters of urine. In my dehydration experiments, I was interested in understanding how much mass reduction I can get by drying the urine, how concentrated my end product was with respect to the liquid urine that I added in the treatment, the drying rate, which I express as the kilograms of urine that I can dry per day per square meter surface area, and in theory, how much urea nitrogen we can recover, which I estimated by calculating the half-life of urea at different drying temperatures. So starting with the results of the drying experiments, I first found that in almost all the cases, by drying the urine, I could reduce its mass by over 90%. And that the drying rate was largely a function of the choice of the drying temperature. And this is because with every 10-degree increase in air temperature, we double the moisture carrying capacity of air. So at 40 degrees, I could dry 6 liters of urine per day per square meter. At 50 degrees, I could dry 20 liters. And at 60 degrees, I could dry between 30 and 40 liters per day per square meter. Now, high drying rates mean that we need small surface area to do the drying. And this can be very important if you want to place a urine dryer inside the bathrooms of dense global cities today, because here space is limited. In terms of recovery of nutrients, I was mostly interested in, or at least focusing only on the recovery of nitrogen, because the rest of the elements in urine are not volatile.